Hello, and welcome back to Physics 141 Classical Electromagnetism 1. So we are now on the second chapter of this course. So in this chapter, we will be dealing with uh, different techniques on how to solve the electric potential. But first, let's review some of the concepts that we need for this chapter. So in the previous chapter, we have discussed about the electric potential. So this will be our main focus for this chapter. So we can directly solve or find the potential using Coulomb's law, using this integral formula here. And we found out in one of our examples that if you try to find the potential inside or outside a sphere of total charge Q, for instance, you can get a single potential function which can describe the potential everywhere. So this is actually our main target for this chapter. We will try to find the general potential function which will describe the potential everywhere for a given distribution, charge distribution. So in the previous chapter, we have also introduced Poisson and Laplace equations, and this is Poisson's equation. It's just the Laplacian of your potential V, and it's just essentially equivalent to the charge distribution in the region. And if your region has no volume charge density or volume charge distribution, then the Poisson's equation becomes a Laplace equation. So for this chapter, we will be focusing on the Laplace equation. So once we know the potential, we can actually solve for everything. So we can solve for the charge density, we can solve for the electric field. So we have equations that can obtain the electric field and potential if you are electric field and the charge density if you are given the potential. So let's now go let's now start with chapter 2. So chapter 2 is formally entitled Special Techniques in Finding the Electric Potential, and we will focus mainly on evaluating the Laplace equation to solve for the electric potential. So our first topic for this chapter, or our first lesson, will be on the Laplace equation and the uniqueness theorem. So in this lesson, we will delve deeper into the Laplace equation and maybe obtain a general idea of how to evaluate or how to solve the Laplace equation and hence the electric potential. So let's now start our lesson. So, as I've said earlier, the Laplace equation is applicable when your volume charge density rho is equal to 0, or if you have a region with no volume charge distribution. So for instance, you have this example. So you have a volume charge distribution here inside this cloud or distribution, and you have electric field outside and potential outside. Now, if you consider this region here and you apply the Laplacian of your potential, you will get essentially your charge distribution. So this is the Poisson's equation. But if you apply the Laplacian of your potential here, then you will get 0 because there's no rho here, there's no charge distribution here, and you will use the Laplace equation. equation. But take note that this potential here and this potential here could just be the same two functions. There could just be one general potential function which describes the potential everywhere, in the region with where there is a charge distribution and in the region where there is no charge distribution. So therefore, you can always choose regions with no volume charge distribution and apply the Laplace equation to find the generic potential function everywhere. So of course, you must couple your solution with the proper boundary conditions so that you can solve the potential using the Laplace equation. So in Cartesian coordinates, this is the Laplace equation. So the Laplacian of v is just the second order partial derivative of v in 3 dimensions, x, y, and z. And of course, your potential at a function at a distance or at r here is r here is what we call the position vector, or the position or the location of your field point. In this case, it's a function of x, y, z. So x, y, z coordinates. Now let's go to the simplest form of the Laplace equation, which is in 1 dimension. So assuming your potential is in 1 dimension, say along x, so the Laplace equation will just look like this. It's just a second total derivative. So take note, the Laplace equation in 3 dimensions or even in 2 dimensions is a partial differential equation, but in 1 dimension it's just a total differential equation because there's only one coordinate. Now this means if your second derivative is equal to 0, then this means that the first derivative must be a constant, say a constant m. So this also further tells you that the potential has the form of a straight line. So your v of x is mx plus b. I think you're familiar with this form. Y is equal to mx plus b, the equation of a line. So your potential will be linear. The slope of this potential will be dv dx. Its rise is potential v. Its run is x. So dv dx. And b here is usually what we call the y-intercept, but in this case it's the v-intercept. It's the value of v at x is equal to 0. So you can call this as v of 0 or v naught or the initial potential. So the solution to Laplace equation has this feature. It has no local extrema. Extrema is either a maxima or a minima. So if you will recall your first derivative test and second derivative test to determine if your function has a maxima or a minima, a maximum or a minimum, the second derivative test tells you that if the second derivative test is negative, it's a maximum, and if it's positive, it's a minimum. But in this case, the second derivative is 0, which tells you that there's no maximum and there's no minimum, or there's no minima. And in fact, the solutions to the Laplace equations, for the solutions of the Laplace equations, the extrema or the maximum or the minimum only occurs at the endpoints or at the boundary. So for instance, in this plot here, the minimum is at this point, the maximum is at this point. So at the edges of your or at the boundaries. And one feature also of the solutions of the Laplace equation is that the potential, say in 1 dimension, the potential at point x is just the average of the potential around that point. So just like this. So in 1 dimension, so along the x-axis, for instance, the potential at point x will just be the average of the potential around this point. So since this is just 1 dimension, so say if the edges of the boundaries from x minus a to x plus a, then the potential at v sub x, or v of x, or the potential at x, is just the potential at x plus a plus the potential of x minus a divided by 2, or the average of the potential of these two around the point x. So in 2 dimensions, Laplace equation in Cartesian coordinates will look like this. So it's still a partial differential equation. And one solution to this is by the method of relaxation. So this is actually a numerical solution. So 1 over 2 pi r, the circumference is, and then you have a closed line integral of v dl. So this is actually just an extended version of the averaging that we have discussed earlier in 1 dimension. So basically, the potential at point xy, so it's now 2 dimensions, x and y coordinates, is the average of the potential around the point xy. So when you say around the point, so that's that essentially describes a circle of radius r, and the potential at this point is the average of the potential within this circle. So again, there are no local extrema, and all extremas are actually at just at the boundaries. So you will know, you will experience, or you will encounter later, that if you have a potential function of a circular two-dimensional sphere, or a circular distribution, then the minimum or the maximum can only be found it's either at the center or at the surface of the circle. So I'd like to emphasize again that this is how a computer solves the Laplace equation, by the method of relaxation. So it's actually a numerical solution. So in 3 dimension, we just extend that idea of averaging, the method of relaxation. So take note that your r, your position vector in 3 dimension, can be in Cartesian xyz, or can be in cylindrical spz, or can be in spherical r theta phi. And this is just the 3-dimensional version of the method of relaxation, or the averaging method. So you have 1 over the surface area of the sphere, closed integral of v dA. So the potential at point r is just the average of the potential around the point. But this now, instead of a circle, we now have a sphere of radius r. And again, same features of these solutions. They have no local extrema. Okay, let's have an example to prove the method of relaxation. So suppose you are asked to find the potential at point P, a distance z from a point charge q. So you have a point charge q, and you are asked to find the potential at this point here, which is a distance z from your point charge q. Of course, we can easily solve this, but we will try to use or verify that we will get the result. So actually, if you solve this is just easy to solve. The potential at this point will just be, since the potential of a point charge is just 1 over 4 pi epsilon naught, then q over the separation distance, curly r. In this case, curly r is just equal to z. So this is actually the answer for this problem. So it's as easy as that. But we will use the method of relaxation just to verify that the method of relaxation actually works. So it's actually a computer program. So using the method of relaxation, so we find a sphere with radius r, and we place its center at the point a distance z from our q. And what we will do is we will try to find the average of all the potentials in the sphere, and show that the average is just the potential at the center, which is just what the equation that I showed you earlier, 1 over 4 pi epsilon naught q over z. So to find the average potential, we need to find the separation distance, curly r, at every point in the sphere. So this is the separation distance vector, or separation distance, curly r. So we use the method of relaxation, where our v here is of course the potential of a point charge, 1 over 4 pi epsilon naught q over curly r, where our r here is the distance from the charge to any point inside the sphere, and that is given by this equation. So we use cosine law here. This is our triangle. This is not a right triangle. This is angle theta. So therefore, this vector here, this side of the triangle here, the curly r, the separation distance, is just equal to the square root of this should be capital R, no? So r squared plus z squared minus 2rz cosine theta. Oh, sorry. Yes, this is correct. This is small. This is small r, because this is the this is supposedly the source position vector. Actually, the proper coordinate for this is r prime, but we'll just get rid of the prime coordinates since there's no conflict in r. So this r here, again, this r corresponds to every point inside the sphere. So we will evaluate r from 0 to capital R, the radius of the sphere. So actually, okay, again, dA here is our differential area in spherical coordinates. So we have actually discussed or encountered this kind of problem before. Actually, I presented a similar equation at the start of this lesson. So you recall that problem, and you get this result when you integrate v and dA, where the separation distance r is given by this one. So you put that in the denominator. So you will get this result. And since obviously for this problem z is greater than capital R, then the absolute value of z minus r is just z minus r. And you get the result. So actually this is not the way to solve this, but I'm just showing you, I'm just proving to you that this method, the method of relaxation, works. So this is how computer programs solve the Laplace equation. But actually you can easily just substitute your separation distance, since clearly the separation distance from the source point charge to the point where we want to find the potential is z. So that one, that this is just a proof to show you that the method of relaxation works. But you are not advised to use this method in finding the potential. So Laplace equation is based on the premise that you can uniquely determine the potential if you apply the Laplace equation. So we will be discussing two uniqueness theorems. So of course, the Laplace equation does not solve itself. You need to have proper boundary conditions if you want to solve the potential using the Laplace equation. So the first uniqueness theorem states that the potential V is uniquely determined in some volume tau. By the way, we need to change our notation for the volume, since I have just realized that in the previous chapter we've been using volume V and potential V at the same time. So we will now be shifting from V to tau for the volume. So in some volume tau, you can solve the potential in that volume if you know the potential on the boundary or on the boundary surface. So if given ang potential on the boundary, then you can solve for the potential in the volume. So a consequence of this uniqueness theorem is that if the potential that you obtain or that you have calculated satisfies the Laplace equation and has the correct value at the boundary, then that means your potential is correct. So if it works on the Laplace equation and if it satisfies all the boundary, then your potential is correct. You got the correct form of the potential. So make sure that every time or after every calculation of the potential, you must cross-examine or cross-check your result with the boundaries and with the Laplace equation. If you apply the Laplace equation, it becomes 0, or if you apply the boundary conditions and it satisfies the boundary conditions. In general, the potential is uniquely determined if the potential is specified on all the boundaries, if there are many boundaries, and if also the charge densities are specified in all of the regions. So for the second uniqueness theorem, this pertains to the electric field and conductors. So in a volume tau surrounded by conductors containing specific charge densities rho, then the electric field can be uniquely determined if the total charge on each conductor is given. So take note that if you are dealing with conductors are equipotential. Surfaces of conductors are equipotential surfaces, which means the potential at the boundary surface of a conductor are equal. So the potential, if you take the potential difference between 2 points in the boundary, you will get 0. So that's it for this lesson. So for the next lesson, we will now try to we will introduce the first method in solving the potential, which is the method of images. So this method will have certain conditions. This will just be applicable to certain conditions. So in summary, we have two uniqueness theorems, which basically just states that the potential can be uniquely determined when you use the Laplace equation, provided that boundary conditions are given. So that's it for this lesson, and I will see you again for the second installment of this chapter. So goodbye.